So good morning, everyone. Can you all hear me right? Yeah? So I hope you had enough coffee this morning because today we're going to cover a slightly dense topic. So we're going to talk about challenges and opportunities for RAN containerized workloads on the edge. There's going to be a lot of acronyms showing up during the presentation. Don't worry, there is a glossary at the bottom for each of the slides. So if you get lost, it should be not a big deal. So first of all, a short introduction for us. Originally, this presentation was going to be co-hosted by two people, but unfortunately, Arunava was unable to come here to Brno, so I will be doing it on mine. But Arunava, he's a senior architect at Mavenir Systems. He's got a lot of experience in the telco environment, from 3G to 5G, and currently he's working on a team that is taking care of containerized DU or RAN in general, radio access network deployments for his company. My name is Javier Peña. I'm a principal software engineer at Red Hat. I've been working for Red Hat for the last 14 years approximately. And I've been working both on the dev and the ops side of the story. So I've been working as a developer, I've been working more in the consulting organization. I have a bit of both worlds. And my current position, I'm working with telco partners and making sure that their workloads, their applications, run properly on top of OpenShift. And I'm also helping them certify their applications on top of the best practices published by Red Hat. So let's get into the topic. So what we're going to see today is this. So first thing, we are going to give you an overview of what a RAN architecture based on containers is. So you will get a base understanding of what we are talking to. Then we will cover the specific requirements that a distributed unit CNF will bring to us. Then we will see the OpenShift functionality for these telco edge deployments and how we can deal with all those specific requirements. After that, we will have a short discussion on how we can reduce the complexity of these deployments using a reference design specification. And finally, we'll have a quick glimpse of what's coming up and what's next for this kind of RAN containerized deployments. So let's get straight into the topic. So when we connect our cell phone to a network and we use it, we usually don't think too much about what's going on underneath. But there is a lot of technology going in the background, and we need to understand what it is to understand what we're going to do with it. So initially, we had something like this. So at the beginning, we had our radio networks, remote radio head. So this is the antenna. Our cell phone was connected to this antenna. And right next to it, we had this first box called a baseband unit. And then, once the information was processed, it was sent to the packet core infrastructure using an IP protocol. Okay? So relatively simple, no big deal. So the key thing here is that both this baseband unit and the packet core were highly specialized, custom-built, custom hardware. Okay? So they had their own custom DSPs, custom processors, custom everything. And custom usually means very expensive. So it was, you would have your hardware vendor providing all the hardware for you, and it would be just like a black box you would use and just go with it. Shortly after that, there was a move to the centralized RAN. So you see it's pretty similar design, but in this case we had this baseband unit was moved away from the side where the antennas were, and we will have bigger boxes where a single baseband unit will be in charge of managing more than one antenna. But still, it was a very similar situation. We still had like both the packet core and the baseband unit were custom hardware, were proprietary hardware, and telco operators will have no control over what's going on underneath. So the next evolution in this environment was the move to virtualized RAN. And this is where things started to get interesting. So instead of having a custom hardware, those functions will be turned into just VMs with actual code running on those VMs. Those VMs would run on general purpose hardware, like an x86 server, which is the ones we have everywhere. And then we can start, since we are running on VMs, we can start running all those virtualized packet core and virtualized baseband units. We can run them on clouds. So this is where OpenStack came into play. For example, in many telco operators, we would see a lot of OpenStack-based deployments where they could run all these all appliances, make them VMs, and then run them in their own clouds. Okay? And then, of course, Kubernetes came in, and the next step of this evolution was moving to Open RAN. So, in this case, what the industry did was several things. So, first thing, they split this virtual baseband unit into more smaller components. Okay? So, there came the DU and the CU. It's a distributed unit and centralized unit. And then there was a move of this old hardware sitting next to the antenna. So we moved some hardware back to the antenna, and it is called the radio unit. And then now we still have the virtualized packet core, but the good thing about this is that instead of having a big full fat VM with a lot of stuff running on top of that, most of these functions were turned into microservices, or smaller services, let's say. So these smaller services are more suited to run on top of Kubernetes, and we can run them on clouds based on Kubernetes. Okay. And then there was the Open RAN initiative on RAN that started building standards and APIs so we could use them instead of having proprietary protocols running in here between the BBU and the packet core. We could use open protocols and open standards so we could start doing more advanced stuff. Okay? So this is what we're going to talk about today. So how we move from proprietary hardware into containers, we can start running them on top of Kubernetes and do fancy stuff with it. So if we move to the right-hand side of the slide, what we see is a typical RAN deployment we have today. So it is pretty similar to this. So we have our cell phone, it's connected to an antenna. We will have one antenna probably somewhere around this building. The antenna is connected to a radio unit, and the radio unit takes care of the initial decoding of the signal. So the signal we transfer to the antenna is then taken by the radio unit, demultiplexed, decoded, and then sent to the distributed unit. And this distributed unit is just an application running on top of Kubernetes, running on top of x86 hardware, and it is placed usually it is located in the same cell tower site where we have the antennas. From there, the information is processed, distributed, and then sent to the centralized unit that is usually run on a data center, much closer to the big data centers. And from there, we send the information to the core network. So this is what happens usually when we make a phone call from our phone or when we access the internet from our phone. Okay? So all this stuff. So now let me introduce you to the edge. So these pictures show us typical cell sites. So here you see there is an antenna, one or more antennas. Okay? It's usually located, could be located in the middle of nowhere. And right next to the antenna, we have like a small building. Okay, so inside this small building, we have something like this. So we have an equipment rack where we can store, can keep all our network equipment and the stuff we need to run our site. We have some limited cooling because we cannot afford to have like the same kind of cooling solution we will have in a large data center. We have to keep it small and relatively inexpensive. Of course, we have power lines to the power grid. If we are lucky, we will have some sort of battery backup. And finally, there is a connectivity going on to the network backbone, to the data center. And this is where things get interesting. So this network connectivity can be done usually via fiber channel or can be wireless. So wireless using microwave or radio, things like that. So what we see is that when we are deploying stuff over here, we're far away from any data center, we have some limitations imposed by this kind of deployment we're doing. So the first limitation is, we are far away from any data center. So in terms of power and cooling, we have limited amount of choice. So we cannot have a large air conditioning. We cannot have connectivity to more than one power provider, things like that. And of course, connectivity is limited and can be flaky. So if you are running wireless and there's a thunderstorm, it might usually have problems. And one of the biggest issues is related to serviceability. So if there is an antenna here at the campus and it breaks down, it's relatively easy to send someone in and fix some stuff. But if you're in the middle of nowhere, you have to send someone with the to fix the broken pieces and do all the maintenance, and then it takes a lot of time, effort, and cost, of course. It is not the same. So then, why did telco operators decide to move away from proprietary hardware and move into containers if it has all these complications? So the first thing is cost. It's what drives the wheel. So when you have a proprietary hardware, you usually have to pay a lot. That usually means paying much more money for the same thing. Instead, if you can move to x86 hardware, what you can do is you can have more people competing for the same. I don't know what happened. Whatever. So yeah, so you have more vendors competing to get the deal. So there you can afford more stuff with less money. Associated to this is to avoid vendor locking. So if you have a chance to mix and match components from different vendors, you will always have a better chance of not being stuck with a single vendor. Of course, in the Open RAN world, we have open standards and open APIs, so you can select and say, I want to have the DU and the antenna from this vendor, but I want to have the centralized unit or the packet core coming from this other vendor. And of course, integrating stuff from different vendors gives you some risk. There is a chance that those pieces of software don't talk to each other properly. But this is usually mitigated by the fact that we have open standards, we have open APIs, and on top of that, it's usually a matter of cost. So if it's cheaper, then you want to assume more risks. And finally, there's a topic of simplified management and lifecycle, because when you have a proprietary hardware, you will have to rely on whatever proprietary management tools the vendor is giving you to manage that deployment. If you run on top of Kubernetes, you will have the chance to choose from different vendors and select the tools that match your needs better. And beyond that, when you're talking about something like Kubernetes, which is a well-known application, a well-known platform, it will be much easier to find people who know how to manage Kubernetes than it will be to find someone who knows how to manage this proprietary management software for this proprietary hardware. Right? Okay. So when we think about the limitations we have for the edge deployments, it's not just the limitations that come because we are running on the edge. There will be some other limitations that are associated to the application itself, the kind of application we're trying to run on top of Kubernetes. And this is where we will discuss those additional limitations. So what we're going to see here next is when running a distributed unit on the edge, right on the cell site, what special limitations we get and how we are dealing with them from the Kubernetes and the OpenShift point of view. So the first and most important thing is latency. Okay? I'm not a big expert on how the 4G or 5G protocols work, but there is one little concept we need to understand very well, and this is the concept of fixed frames. So whenever our phone is connected to the network and we are doing a phone call over LTE, or we are connected to the internet, there is a fixed frame where all the processing needs to happen. Okay, from the time where we send a packet to the antenna from over here. Okay, when this packet is received, this packet needs to be decoded and then processed and then sent elsewhere. So there is a fixed amount of time where we need to do all this stuff, all this work. Okay, so when we speak about 4G, it's about 10 milliseconds approximately. When we are on 5G, it's much smaller. It's somewhere between 8 to 15 microseconds. So that means that in these 18 to 15 microseconds, it goes like a clock, like tock, 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 tock. And everything needs to happen in that amount of time. If we lose that frame, that amount of time, because we need to spend more time on the coding or on the processing or whatever, then we get dropped frames, we get dropped calls, we get connectivity problems. So we need to be very, very specific in this. So as a result of all of these, we get some very custom low latency requirements. This means we will usually need to run the real-time kernel. Okay, this is a common requirement. Another thing we will have to do is we will have to reserve CPUs for the application. So the application doing all of these needs to avoid any kind of interruptions coming from the operating system, from an interrupt, things like that. So the operating system needs to stay away from those CPUs. And of course, we will need to have direct access to the network stack because we want to bypass all the abstraction layers that go between the container and the hardware itself. So next thing, we will need to have some very high precision timing. Similarly, it's tied to the previous requirement. Because we have fixed frames, we need to be able to synchronize the time between some of the pieces in this network very precisely. Usually in the IT world, we would use NTP because it's the network time protocol. However, NTP is not enough because its precision is in the range of microseconds. And we need to go down to nanosecond level precision, which is much more precise. So we need a different protocol. It is called PTP, Precision Time Protocol. I could talk for hours about PTP, unfortunately for you. However, there's just two things we need to keep in mind. The first thing is that PTP usually requires hardware support from the network card. So the network card needs to support certain hardware timestamping bits to work with PTP properly. And on top of that, we have some NICs include GPS or GNSS hardware for PTP support. So it means there is a GPS chip embedded in the network card, just like the one we have in our cell phone, for example. This GPS chip is connected to a GPS antenna, and it is receiving information from the GPS constellation, and it uses the time information coming from the GPS constellation as a very precise time source to synchronize the time across the network. Okay. So we will need to have some support from the operating system point of view for this custom hardware. On top of that, there is more custom hardware we need to use. Again, I'm not going to bore you to death with all the details, however, there is one thing we need to know. So both 4G and 5G protocols use a thing called forward error correction. So this is a protocol with parity checks that can be used to detect and correct some parity errors in the information. The important thing here is that since we have very high bandwidth and low latency requirements, as we said before, we need to be able to transfer a lot of information and to check all those parity bits all over the place. And this is a very CPU-intensive calculation. So since we have to do something very fast with very low latency, and we have some operation that is very CPU-intensive, we will usually need to have some custom hardware accelerators. So each vendor has created their own custom accelerator, and what this stuff does is basically they just, for example, the Intel stuff is an FPGA-based, I think, approach, where they have some very, very quick hardware just to do this forward error correction. Thing. So we will need to be able to manage that hardware. We will need to be able to expose that hardware to the containers and be able to use it. And then the final one is large-scale deployments. So this is, let's say we have a single server running on each of the 4G or 5G cell towers we have in the country. So in the Czech Republic, we would have like 100,000 nodes just here. So that means not only 100,000 nodes, but 100,000 sites. All of them with their own connectivity issues and their own connectivity stuff. If you go to Spain, it's like 250,000, 500,000 in India. If you go to the US, it's like 5 million. So you guys, I guess you know where I'm coming to. You need to be able to deploy, manage, monitor, all of that. And it's not as easy as it would be if we were running on a single data center. We have to be able to spread the information across thousands or millions of sites where we have a single one or two servers. Okay, so we need to be able to manage all of this. So, how do we do all this stuff in OpenShift and Kubernetes in particular? So, for the low latency tuning stuff, there is an operator called the node tuning operator, which exposes a custom resource called the performance profile. So this performance profile allows us to configure a lot of the low-level tuning stuff that we would normally go and configure manually on our server by hand, by editing some configuration files. So it allows us to set kernel parameters, select if we want to run the real-time kernel, select which CPUs we are going to reserve for exclusive operating system usage, which CPUs we want to select for exclusive application usage, things like that. There's a lot more stuff we can do. But in general, we try to keep all this tuning in a single custom resource, or two custom resources managed by a single operator, so that everything can be centralized. You don't have to go edit my files manually everywhere. So for custom hardware, we also have some operators going on. There is an SRAOD operator that can be used to partition a network card into multiple visual functions. And then we can take those visual functions and then expose them directly as resources to the containers. So our container can directly bypass all of the abstraction layers and talk directly to the hardware. So we are getting a lot of latency reduced output. So for example, one of the accelerator operators is the containerized FEC operator, and it does something very similar. So it allows us to configure the hardware for the Intel accelerators. It allows us to partition the accelerator into smaller pieces, and then we can expose it as resources to pods. So we have all the pieces exposed directly to the pod. Finally, for precision timing, there is a PTP operator again. We can use it to manage PTP-capable hardware. So it also exposes a custom resource, PTP config. We can use this PTP config to configure the different topologies we can use for PTP, and then make sure that the timing is synchronized correctly among our network. And then, again, we were talking about how to manage and deploy this at this scale. So what we do at the Red Hat side is to use GitOps to manage all the edge nodes. There is a product called Red Hat Advanced Cluster Management for Kubernetes, which includes a lot of operators. It includes Argo CD, it includes the assistant installer, topology, web second manager, and some others. And we like cover them, we wrap them up, and we use a GitOps approach to do all the management. So what we do is, what we will have is a Git repository with the site installation data and the cluster information, the cluster configuration information. Okay, we will have a lot of YAML files sitting over there, and whenever there is a change to any of those YAML files, then the GitOps part comes in. It will configure the required resources, and it will tell the required operators to do their job. And then, after doing that, we will get our clusters deployed first and then configured using these policies. Okay, so this is a very high level overview. For the two operations, as we said, there will be policies we can use to configure stuff. We can tell Argo CD to set up an operator, we can tell it to set up an application, we can tell it to configure whatever we need to do on the OpenShift clusters. For application deployments, we will use either Helm charts or operators. And again, we will include all that information into the Git repository, and then use the GitOps approach to make sure that it is all deployed. We don't need to go manually to all these thousands of nodes to deploy the application because it's not so stable. All right, so with GitOps, what we can do is we can make sure that the different clusters we have in our single deployment are connected together and they're working fine and they're all more or less using the same configuration. But let's say we are a company and we have multiple different customers, and we want these different customers to have a very similar configuration, to have consistency in those configurations. We make sure we don't have those snowflakes running around that cause all those troubleshooting problems. So from the Red Hat point of view, the Telco team at Red Hat came with a concept called the reference design specification. Okay? So a reference design specification is just a way to ensure consistency. What we want to do is we want to give our partners and customers a known good starting point, which they can use to build their Telco stack on top of that. And of course, by having a common configuration, we will be reducing the risk of those deployments. So you know that what you're deploying is going to work first time without having to go manually and change a lot of stuff. So the RDS, as we call it, is basically a specification document. It's part of the official documentation. And it includes a set of configuration resources for different use cases. There's one for the RAN, there's another one for the Telco core use case. And the important topic around this is that all of this is continually tested and validated against a set of KPIs. So what we can guarantee you as a Telco partner or customer is that once you deploy stuff using our RDS, you will have a latency below a certain threshold and that your application will be able to run correctly and things like that. So, as usual, it is expected that one size will never fit all, so that's life. So the specification itself is covering for some known variations. So there will be some optional configuration components, and of course there will be some PTP topologies and stuff like that. So, and of course there will be some variations depending on the application we want to run on top of OpenShift or Kubernetes, because we might have Our CNF will require a kernel parameter X to have this value, but the reference design is saying, no, you should have this other parameter value. So for this, of course, it is also easy to drift, because when we are doing troubleshooting, when we're doing some testing, it is very easy to say, yeah, to change stuff without and forget about that, or without letting someone else know. And this is usually something that causes a lot of trouble. So the team created a kubectl plugin called Cluster Compare, and this plugin is allowing us to take the live cluster configuration and state, compare it against the reference templates, and then give us an evaluation. It basically tells us, okay, in this YAML file, you change this parameter to this value. In this other YAML file, you change it to this other value from the reference. The important thing about this is that once you have the information, you can decide what to do with that information. You can check the evaluation and say, all right, this is an expected variation, no problem, we can live with that, or this is something we want to do. Or on the other hand, yeah, this was some test done by Javier, and he made a mistake and he never reverted the configuration value. Let's fix it. Okay? So this is the importance of it. Finally, because I'm running out of time, so what's coming next? So at the edge. So the first thing we will have to do in the future is, of course, enable new hardware. There will be new CPU generations coming, newer Intel CPU generations, for example, come with the accelerator built in, so we will have to be able to manage all of that. GPU acceleration, of course, as soon as they find a way to apply that in the edge, someone will want to use it, and we'll have to be ready for that. ARM support is also important because we will want to run our edge deployments with a lower power envelope, because it will give us a lot of savings. So there are a lot of people who are investing time in this. Of course, you will be able to come out of this presentation without hearing the word AI. There's also a word on AI in Telco, but most of this is not related necessarily to LLMs. There's a lot of machine learning being used right now to improve network performance, to detect anomalies of things that are not behaving the way as they should in the network, and also for traffic pattern prediction, so you can be prepared in advance and make changes or adjustments to your network configuration before something happens. And finally, we will, of course, continue growing. We will have larger scale deployments. And there is currently one area of standardization in the Open RAN space around management where Red Hat is being very active. So we want to standardize the way APIs, let me rewind. So we want to create standards and well-defined APIs to be able to manage those environments. All right. So that's it for now. Anyone has any questions? Did I bore you to death?
Let's repeat the questions. I have no idea why this turned off. So
yeah, okay, it's back.
Okay, thank you. Thank you very much for your presentation. I have a question. Imagine we have a 4G solution, right? And we try to upgrade to OpenShift, right? But existing solution relies on some old hardware for the antenna that's like virtualized. Currently, it's just a module to old ISX6 in VMware, so it can be PCI to the Linux doing the DU processing. Is there something in the OpenShift for virtualizing these PCI cards or drivers for them?
For PCI cards, so that depends on the PCI card. So so let me think. I would need to check actually, to be honest. I don't know. So if it's very, very custom hardware, I think there is a chance, there is a way to expose hardware directly to pods, but I will need to check. That depends. So if you can talk to me later, we can because I have to check that.
I was particularly interested in the precision time protocol. Is that something where Crony is involved, like in normal time synchronization in Linux system, or is there a separate project that handles it, or how that works?
Okay. I have a backup slide for this.
Nice.
So yeah, so long story short, so there is a Linux PTP project upstream where you have all the a set of binaries that take care of all the different pieces of here. So we have PTP4L, PHC2C, and TS2PHC. So in short, it relies on hardware timestamping at the NIC level, and then you have different daemons that, depending on the configuration where you're getting the signal from, you can either get the configuration from the NIC, you can get it from the GPS hardware, and then you have separate daemons taking care of. One of them is adjusting the offset in the NIC. PHC2C is taking the offset, the time information from the NIC and then adjusting the system clock with it. And then PTP4L is used to get the offset information from the network. And you have another configuration. So in short, you have the Linux PTP project takes care of all these different stuff.
Okay, thanks.
Hello, thank you for the presentation. I have a question regarding the resource or hardware usage. If you can, or what is the recommended way to measure the hardware usage on the CNF RAN solution? How we can measure the CPU usage and memory usage. What you can recommend for when you use Kubernetes?
So to reduce the usage, it really depends on your application. So first thing you will want to do is offload as much as you can to specialized hardware. So if you can use a custom hardware to do the decoding part, use it. If you can use these accelerators for the forward error correction, use it as much as you can. And then, depending on the framework you're using to build your CNF application, then you will have to work with your provider.
Okay, there is no one. Okay.
So if you're the vendor, instead of, for example, you're not using Intel FlexRAN or something like that, you will have to profile your application and make sure that you are reducing the CPU load as much as you can.
Okay. Okay, we have There's a lot of pods in CU and DU in our solution, and we wonder how to solve the issue with some measurement and okay, thank you.
In general, for example, one thing you will want to do, especially in a DU application, is to avoid going to the kernel as much as possible. You want to stay in user space 100% of your time.
Okay.
As soon as you exit to kernel space, you get into trouble. You lose timings. There's a lot more unpredictability over there.
Okay, thank you.
So, we did it on time, right? So, in any case, I'll be around the whole weekend, so if there's anything you want to talk to about with me, just ping me, and I'm happy to answer to whatever I can. Okay? Thank you very much.